our study, we focus on developing an interpretable model with handcrafted features to predict perceived visual complexity. Visual complexity is conventionally defined as the level of detail or intricacy contained within an image. Recent studies have shown that using the number of objects and the number of semantic image classes can achieve surprisingly high correlation scores with human annotated ground truth complexity. Building on this prior work, we introduced new low-level visual features, multi-scale Sobel gradients and multi-scale unique colors. The main idea behind multi-scale Sobel gradients is to measure patch symmetry by applying a Sobel kernel at multiple scales. MSG values are low when the image consists of highly symmetrical 3 by 3 patches and increase as the image becomes more asymmetrical. Our approach outperforms traditional methods such as edge density, as well as the patch symmetry metric introduced by Kyle Davidson et al. Moreover, the multi-scale approach shows statistically significant improvements over the single-scale version of our method. Next, we introduce multi-scale unique colors, a reformulated, multi-scale version of a colorfulness feature originally proposed by Teresa et al. This metric counts the number of unique colors in an image after quantizing the RGB values to reduce sensitivity. For example, some images may have similar MSG values, but differ significantly in MUZ values. With the inclusion of MSG and MUC, the baseline model's performance improves significantly, as shown in our results. We calculate each feature on the image, and then train a linear regressor using these features alongside the number of objects and segmentation classes from previous work. But what about semantic features? Familiarity has been shown to be negatively correlated with perceived visual complexity. For instance, consider these two images. Although their visual features are quite similar, the perceived complexity of the first image is 55, while the second is rated at 73. So, what accounts for this hidden dimension of visual complexity? To explore this, we curated a new dataset called Surprising Visual Genome by selecting 100 random and 100 surprising images from the visual genome. We then obtained surprisal scores using a large language model via chain of thought prompting, explicitly asking for reasoning to maintain interpretability. We conducted a prolific experiment where participants were asked to choose which of two images appeared more visually complex. We converted these pairwise comparisons into 0-100 scores using the Bradley-Terry algorithm. You can find the experiment instructions and sample images from SVG in our materials. As seen, SVG contains a variety of normal, complex, non-complex, and surprising images. According to the survey results, the surprisingness of an image was one of the key contributors to how visually complex participants rated it. On the SVG dataset, the baseline model achieves a correlation score of 0.78, which increases slightly to 0.79 with MSG and MUC. However, incorporating the surprise score boost performance to 0.83, matching the best supervised model by foam. Our final model, which combines MSG, MUC, and surprise scores, achieves a correlation score of 0.85, outperforming the supervised model using only interpretable handcrafted features. As a result, our final model achieves significant improvements over the baseline across all datasets we evaluated. Excluding datasets used to train the best supervised model, our approach matches or exceeds its performance on 5 out of 8 benchmarks. To conclude, we introduce MSG and MUC, which outperform previously proposed handcrafted features. We demonstrate that the perceived surprisingness of an image is a significant contributor to visual complexity. To support this, we curate a new dataset called Surprising Visual Genome, which includes human-rated complexity scores. You can find the dataset on Hugging Face. For more details, please refer to our paper. Thank you for your time.